Hey guys, and welcome to another engineering mechanics lecture. Today we're going to be discussing how a object either rolls or slips, or a combination of both on a surface. So, what does this mean? Well, an object. Let's say that this is a round object. A rolling object will maintain an instantaneous center at the point that it contacts the floor. That means that at all points in time, the velocity of this point relative to the floor is zero. Now, if an object is slipping, then this point will have some velocity in the direction of motion. Now, how do we calculate this? How do we figure this out? Well, there's two key components here. The first is the static friction of an object. Now, the static friction of an object is less than or equal to the coefficient of static friction times the normal force that the object experiences. Now, note here that this is less than or equal to. So we'll have to figure out what the exact value of this static friction is, since it's not simply equal to this formula. However, kinetic friction can simply be given by the kinetic coefficient times the normal force. Okay. Now, this is best demonstrated through an example. So here we have a problem, a simple problem, where we have a circular disc with a groove in the middle with some string attached. So we've got tension on the string and a force being applied of value T, which is 30 newtons. And that's offset by this radius here, which we've defined as 0.05 meters. Now the total radius of the cylinder is 0.2 meters. Let's define that as R. And we've also defined its mass and its radius of gyration. Now, note here that the static coefficient of friction is higher than the kinetic coefficient of friction. And that's generally true for most of the cases. So let's start off here by drawing our handy-dandy free body diagram. And we'll just get rid of the floor. Oh, can't do that. Alright, we'll just ignore the floor at the moment and draw around it. So we're going to have a normal force acting upwards here. And we're going to have a weight force acting through the center of the cylinder. Okay. And we're also going to have a friction force in the opposite direction to the motion. So we're going to have this friction force here, which we'll label as F. Okay, and obviously we've got this tension. So force sum. So if we take our convention of y is upwards and x is in the positive direction to the right, then we have in the y direction MAY is equal to, well, what do we have in the y direction? We have normal force acting upwards and the weight force acting downwards. Now, note here that since this is a solid surface, the cylinder can't really accelerate downwards, so this here is 0, and we can simply say that the weight is equal to the normal force, which is of course mg. Okay, so now we go on to the horizontal direction, and we go to the sum of forces in the x direction. Again, we've got our mass times acceleration, and here we have this tension force acting to the right, and the friction force acting to the left. Now we can't simply substitute n times mu yet, and we'll explain why in just a second. The last equation we can form is the sum of moments equation, and we'll take this about the center of mass g. Okay, so we'll have I bar times alpha is equal to, now if we use our convention as counterclockwise is positive, then we have this tension force acting at distance r, and we have this force here acting in a clockwise direction, that distance capital R. So F times R. Now, why can we not simply substitute mu times n here? Well, we first need to assume that this object is purely Roland. Now, because of this, we know that f is going to be less than or equal to a certain value, but we don't know what that value is yet. So what we can do is we can calculate the max value that f can take. So f max is equal to the static coefficient times n, which we have discovered as mg. And this, if we substitute the numbers in from above, it's 0.07 times 25 times 9.81, and this gives us the value equal to 17.168 newtons. Now, this is our maximum value of static friction. If we calculate this f to be greater than this value, then we know that this object is not rolling, because static friction cannot support that. If it's less than this value, then our assumption is correct. So this here is our assumption. Okay, so the next thing to do is, once we've assumed that the object is purely rolling, that means we have a instantaneous center at the floor, and we can simply say that the acceleration of the center of mass is equal to alpha times the radius to the center of mass. Since we have defined the positive direction to be counterclockwise, but we have AX to be accelerating in a clockwise direction, this is going to be negative. So if we substitute this into our above equation and rearrange, I'll leave the algebra up to you, but we get an equation F is equal to T times MRR plus I about the center of mass, all divided by mr squared plus I bar. Now at this point we haven't calculated I bar, but we know that I bar is equal to, or I about the center of gravity, is equal to m times the radius of gyration. Now if we substitute this in, it's interesting to note that the masses on both the top and the bottom cancel out, and the resulting equation is just related to all the radiuses. So in fact, the static friction does not at all depend on the mass of the cylinder. And this is an interesting relationship, because obviously the kinetic friction does depend on the mass, as it's calculated using the normal force. But anyway, if we substitute the values for this, we find that F is equal to 19.38 newtons. Now this is greater than the static force of friction, which can be supported, as we've calculated before, to be 17.168. And therefore, this assumption that we've made here is in fact incorrect. Now, since the cylinder is not rolling and it's sliding, then we can simply calculate F as the kinetic coefficient of friction times the mass times gravity, and if we substitute these numbers in, 0.05 by 25 kilograms by the acceleration due to gravity, we get a value for F which is equal to 12.16 newtons. And again, we can simply substitute this in to the equation that we've calculated above already, and here the only unknown for the acceleration is the acceleration itself. So that's simply acceleration is equal to the tension in the string minus the friction force divided by the mass of the cylinder. So 30 minus 12.16 all divided by 25, and we get a final acceleration that's equal to 0.714 meters per second squared. That's really all there is to it. Essentially, when you encounter a problem like this, or any problem that has rolling, you always check first to see if it is a pure rolling problem or if there is going to be any sliding involved. And that's it for today. If you have any questions or comments on the video, please leave them in the section down below, and thanks for watching.